And yesterday we finished by relating polarization to the integral of the Berry phase over a one-dimensional Brillouin zone. And before I proceed to an example, let me just mention one thing that I didn't last time. Namely, there is an inherent ambiguity in definition of polarization, namely that P is defined only modulo electron charge E. And this is simply because one can always add or subtract an extra electron from the end of a one-dimensional system without affecting the bulk, right? So one can always add or subtract an electron from the end without affecting the bulk. So only the fractional part of polarization is determined by the bulk. And it's satisfying to note that the Berry phase has exactly the same ambiguity. Namely, under gauge transformation, UK goes to e to I phi k. I should not write vectors because this is 1D. With phi pi over a minus phi minus pi over a equals 2 pi times n, we have polarization goes to P plus NE. So the point here is that I can perform a gauge transformation that is perfectly legitimate, perfectly smooth, except that imagine that this phi is such that it does not go back to itself after traversing the full Brillouin zone, but changes by 2 pi times integer. Then this exponential function still is perfectly smooth, right? Because e to the I 2 pi n is always 1. However, you can see that if you plug this gauge transformation into the formula for the polarization, you will see that it changes by n times e, where this n is exactly the same n as you put in the gauge transformation. So both the polarization and the Berry phase have the same ambiguity, and we will see that realized in the example that we studied today. Are there any questions about this or anything that we discussed last time? So let me proceed to the example of a 1D system where this physics plays out. And the example goes under the name of polyacetylene. And Su-Schrieffer-Heeger model. So polyacetylene is a long organic molecule similar to polyethylene that one uses in many common plastics. And polyacetylene molecule is basically a backbone of carbons that has this zigzag structure with some hydrogens attached to it. For our purposes, really, we're only interested in carbons. And it has this interesting property that it's always dimerized. So in nature, it's always found in a dimerized state. What this means that I'm drawing these double lines and single lines, and these double lines are somewhat shorter than the single lines. Okay? And the molecule comes typically in two conformations. You can see that there's two dimerizations that are permitted. Maybe I can, okay. I can use color here. So let me mark these double bonds in yellow, right? And then there's another conformation that has the opposite pattern, where the double bonds are on the other other bond. Okay. Now the physics behind why this is so is also interesting. It's basically a interplay between electronic energy and elastic energy. And in 1D, you can show that generically things want to dimerize whenever this is permitted by symmetry, and polyacetylene is a simple example of this. For our purposes, we're going to model this polyacetylene as a simple tight binding model for electrons hopping along these carbons, and this is the Su-Schrieffer-Heeger model that they formulated back in the 60s. So basically, what we'll do, we define a unit cell, and the unit cell will be this with length A, and then on each side we define a creation and annihilation operator. So this unit cell will be labeled by index J. The next one will be J plus 1, and so on. And we have two possible sites in each unit cell. So we label the two electron sites as CJ1 and CJ2. Okay, so like this. And then our tight binding model will be simply allowing electrons to hop between nearest neighbors. And to allow for this dimerization, we call this bond T plus delta T. And this one we call T minus delta T, where T is some hopping strength and delta T accounts for dimerization. So basically, because these two atoms are a little closer to one another, the wave functions overlap a little more, so we expect the hopping amplitude to be somewhat stronger, and on the other one, it's going to be somewhat weaker. And we can immediately write the corresponding Hamiltonian. So it's going to be sum over all unit cells J, and then I have a first type of hopping C dagger 1J, C 2J plus T minus delta T times C dagger 1J plus 1 C 2J plus HC, and HC, if you have not seen this, means just a term that is Hermitian conjugate. So I basically take a Hermitian conjugate of these two and add it to the Hamiltonian. So once again, this term simply corresponds to hopping along the stronger bond from CJ1 to from site 1 to site 2, and this term corresponds to this weaker bond from hopping from Cj plus 1 to Cj2. Okay. Now, this conformation will then correspond to delta t greater than 0, and this one will correspond to delta t less than 0. And we can now easily solve this Hamiltonian, again, by Fourier transforming. So let's do that. We define Caj as sum over k e to the I kj Caj, where a takes value 1 or 2. So either one of them we Fourier transform. And under this transformation, the Hamiltonian will have this form, sum over k h a b of k is c dagger a k c b k. And since we have 2 degrees of freedom per unit cell, this is a 2-level Hamiltonian, which so this is a 2-by-2 matrix in these indices 1 and 2, right? So I can write this 2-by-2 matrix as h of k in our previous notation, d of k dotted into sigma, right? We argued last time that any such 2-level Hamiltonian can be written in this form, and we can now easily find what these vectors are. So this is just done by simply finding the matrix elements here. And again, I will just give you a result. Hopefully, everybody can do this to their satisfaction. And again, I shouldn't be writing vectors here because it's a one-dimensional problem. So dx of k, one finds to be the following. It's t1 plus t2 cosine k times a. dy of k, one finds to be t2 sine k of a. And dz of k, one finds to be equal to 0. And I have defined here t1 to be t plus delta t and t2 to be t minus delta t, just for a shorthand. And you can see why this is so. So first of all, if I have nearest neighbor hoppings, I only have always hopping that goes between site 1 and site 2, or site 2 and site 1, and that's why my Hamiltonian has no diagonal terms. This would correspond to hopping from site 1 to site 1, for instance, from here to there, but I don't allow that. And then these guys here, sine and cosine, simply correspond to the fact that these guys are shifted by one lattice spacing. So when I do a Fourier transform, these j's are offset by a, so I get some factors of sines and cosines as usual in a tight binding model. Does that sound reasonable? Okay, so now I can easily calculate the spectrum according to the general recipe that we derived last time. And the spectrum E of k is simply plus minus the length of this vector k. And we can easily calculate that length of that vector. And it's simply plus minus of t1 plus t2 cosine k squared plus t2 squared sine squared k. And what I'm doing here, I'm taking my a equal to 1, just so that I don't have to write Ka every time. So I'm taking just my unit cell to be of length 1. And I can always restore a general A if I want to by simply replacing K by K times A. Doing just a tiny bit of algebra here under the square root and using some trig identities, I can rewrite this as plus minus square root of T1 minus T2 squared plus 4T1 T2 times cosine squared K over 2. And you can see how this happens. If I square this up, then I get cos K squared plus sine K squared. That gives me 1. And the rest can be reorganized in this fashion. And this is a useful way of looking at this spectrum, because it tells me that the spectrum will be gapless when T1 is equal to T2, but will have a gap when they are different, right? Plus, I know that this is my delta T, so whenever the system is undimerized, it's gapless. However, when it's dimerized, it has a gap. So let me sketch this spectrum for you for the two cases. So for delta T equals 0, this is my K from minus pi to pi. This is my one-dimensional Brillouin zone. And when this delta T is equal to 0, then I can just take a square root of this cosine K over 2. And I find that I have just two branches like this. This is just my cosine K over 2. And they should be symmetric if I drew this right. On the other hand, when I allow for non-zero dimerization, so this is K, this is EK, so this is delta T non-zero, then on the same graph, I see that where previously my cosine was allowed to go to 0, I will have to add this term in quadrature, so the thing will not go to 0 any longer, and will look more like this. Okay. Again, it's not quite symmetric, but let's live with that. So in the generic case, when dimerization is non-zero, which is the physical case, which is the case for physical polyacetylene, and if I have exactly one electron per unit cell, as again is the case for polyacetylene, I will have an insulator because the lower band is filled, the upper band is empty, and I have a band gap, and this band gap here is twice delta T. Okay, so in other words, whenever delta T is non-zero, I have a one-dimensional insulator with a band gap, and all this physics about polarization applies because I can now calculate the polarization and see if there's something interesting happening. And what we will find is that delta T equals 0 corresponds to a topological phase transition between a topologically trivial and topologically non-trivial phase that will be distinguished by, not by symmetry, but by this topological invariant that is related to polarization. Okay? Any questions about this? Okay, so let's look at the Berry phase. So we have the spectrum, and let's look at the Berry phase. And we can now do the calculation of the Berry phase, but in this case, things are sufficiently simple that we can actually deduce this Berry phase just by looking at pretty pictures, okay? And remember, the Berry phase, according to our previous discussion, is just half of the total angle swept by this vector d. Where's my vector d? Well, unit vector d on the three-dimensional unit sphere. Okay, so let's study unit vector in the direction of this vector d, and let's see if it sweeps any angle on the unit sphere. Now, our analysis is aided greatly by the fact that only two components of that vector are non-zero, right? dz is 0 here because we're prohibiting next nearest neighbor hoppings, which means that vector d only lives in a two-dimensional plane. Okay, so to analyze the Berry phase, look at d of k, and in particular, we want to look at the unit vector d of k, which is just shouldn't write these vectors here, dk over absolute value of dk. So let's first look at dk, and like I said, they only live in xy plane, so I don't have to worry about the z direction, so that makes the analysis simple. So let me draw this dx dy plane, and what I'm plotting here is now the full vector d of k as it traverses the Brillouin zone. And now look at this expression here, right? So I have a two-component vector, which there's some constant here, but it depends on its x and y components behave as cosine and sine of some parameter, ka, that varies from minus pi to pi. So what sort of curve is this? This is just a circle, but it's a circle because of this T1, which is offset from the center by this amount T1, right? So it's just a circle, and it so happens that when delta t is greater than 0, the circle is offset in such a way that it does not contain the origin, right? Just because when delta t is greater than 0, then t1, the offset is larger than the circle radius, t2. So the situation looks like this. Whereas in the opposite case, when delta t is less than 0, the same picture can be drawn as the circle has a center somewhere here, and it now contains the origin. Right? And this will actually be very important. So origin is here. So now let's think about the unit, how the unit vector behaves. So here we discussed the behavior of the vector itself. How does the unit vector behave? So this is now axes for dx unit vector, dy unit vector. So imagine in this first case, right, what's happening here. So my vector d goes from here to some point on this circle. So this is my vector d. And as I traverse the circle, this unit vector always points only in this direction, right? So what the unit vector will do, it will just do this, right? It will go up to the end point, which happens when the d vector is just tangent to this circle, and then it will go back down like this. Okay, so this is the behavior of the unit vector in this case when delta t is greater than 0. However, in the opposite case, when delta t is smaller than 0, then one can see that the vector d just goes all the way around the origin, right? So the unit vector describes a circle centered around the origin. Okay? Now, if you now can elevate yourselves to 3 dimensions, right? So here we have just a xy plane of a 3-dimensional plane of a 3-dimensional space, and we're trying to decide whether this unit vector d, what angle it sweeps on this unit sphere, right? So it's clear that in this case the angle that is being swept is exactly 0, because the unit vector just goes in xy plane and does this, right? So it doesn't sweep any 3-dimensional angle. On the other hand, in this case, if you think about 3-dimensional sphere, this unit vector goes like this, so it sweeps exactly half of the sphere. So here, the angle is 2 pi. Is this clear? One could do this as a calculation, but this is much prettier, I think. One could actually plug in the formulas and do the integrals, but this actually tells you what's happening, whereas that calculation just exercises your right hand if you write with the right hand and part of your brain. So in this case, the gamma c is 0 because it's just half of omega, and the polarization is 0 as well. So this, we say, is a topologically trivial phase. Doesn't lead to any polarization. On the other hand, here, gamma c is 1/2 of omega, which is pi. And the associated polarization is e over 2 pi times gamma c, which gives me e over 2. And this we might call topological phase. And it's a topological phase with charge q equals e over 2 plus minus bound to the end. Okay? And notice that we only considered an infinite chain here, or a chain of polyacetylene with periodic boundary conditions, because we went to Fourier space and we didn't really explicitly consider any end, right? So we just considered bulk of the system, yet we arrived at this result, which is presumably telling us something about what happens at the end of the chain in the geometry, which is finite. So this is kind of cool. And if you don't find this cool, then you can go home, because it doesn't get any cooler than this. We will see some other examples of this, but they are somewhat more complicated, and this kind of detracts a little bit from the coolness of the argument. Okay, so let's see if this makes sense, right? And how can one interpret this in real space? And in fact, there is a simple limit in which one can see this, this fractional charge actually explicitly. So let's draw some more pictures. So consider the case of extreme dimerization. And by extreme dimerization, I mean delta T is equal to plus or minus T. Okay? So it's as dimerized as it can get, meaning the dimerization itself is the same as the hopping element, which means that I have either T1 or T2 equal to 0, right, depending on the sign there. And let's draw the appropriate pictures here for 4 dimers so that it's simple. So let's start with delta T equals plus T. In this case, that's the upper drawing there. And what I will find is that I have my backbone like this. And let me draw it once again for 4 dimers. And in this case, I only have this bond that is non-zero, right? And the other one is just 0, so I don't draw anything there. Now, I have 4 dimers, and in order to get an insulator, according to our previous analysis, I have 1 electron per unit cell. This is my unit cell. So what I do, I put 1 electron here, 1 electron there, 1 electron there, 1 electron there, 4 electrons, and I end up with 1/2 electron per site. Okay, and clearly polarization here is 0, right? There's nothing at the ends. Every site here has the same charge density. Polarization is 0. Okay, so now let's consider the same case. So this is the trivial case, and indeed it agrees with this conclusion here that in the case when delta T is greater than 0, I should get topologically trivial phase. So how do we get something that is non-trivial? Well, let's draw the situation. So delta T is equal to minus T. This is the extreme dimerization in the opposite direction. So now I have these bonds that are strong, and the other ones are all 0, right? And now I have my 4 electrons, so I put them as uniformly as I can. So I put 3 of them here, right? But I still have 1 left over, so that I have a neutral system. I have to place this electron somewhere, and I can either put it here or there. I cannot put it anywhere else, so I put it here. But what this means is that, say, if I put it here, I have, again, here in the bulk, I have 1/2 E per site, right? And here I have E per site, and here I have 0, which means that from the point of view of this uniform chain, this extra electron means that I have plus 1/2 electron. So the extra charge, the surface charge, QS here, is plus 1/2 electron compared to what it should be, right? It should be like here, it's 1/2 electron per site, but I have full electron there. So this surface charge is plus 1/2 E. This one, let's call it QS prime, this is charge here, is minus 1/2 E because it's 0, so that's 1/2 less than what I should have had. Yes, question?
Could you remind me what delta T is physically?
Say it again?
Could you remind me what delta T is physically?
Oh, so delta T is just a dimerization which so what the empirical fact about polyacetylene is that when you look at it, these bonds are somewhat shorter than these bonds, right? Now, if you want to model the behavior of electrons, as in the Su-Schrieffer-Heeger model, then you have to conclude that because the hopping amplitude for electrons depends on how much the wave functions overlap of the orbitals, you conclude that on shorter bonds, this hopping amplitude will be somewhat larger than on longer bonds. So we model it simply by saying that this delta T is here, and there's minus delta T on the other one. So what I'm talking about right now, this extreme dimerization case, is somewhat unphysical in that it does not apply to real polyacetylene. But as a limiting case, the analysis should still be valid, the one with the polarization. And indeed, we see here that it is valid in this very simple, again, pictorial representation. We can see that this polarization 1/2 E plus minus actually arises. And to continue, I could decide, of course, to take this electron and put it instead here, and then I would have a polarization minus half an electron, and that's precisely this polarization ambiguity that I mentioned before. Now, of course, you can object, this is just a cartoon picture, does not really apply to polyacetylene, where this delta T is typically much smaller than T. However, if you want to, and this is a very simple exercise, actually, that I assign as a homework in my course at UBC, where we have more time to do this, you can actually numerically solve this simple 1D model and calculate the charge density for any delta T, right? And you find that, indeed, this behavior persists. As long as you have one pattern of dimerization, you have one pattern of polarization. As soon as you go through this topological phase transition, that disappears and everything is uniform. So here we see it in the extreme case, but the point is, even when I allow for delta T to not be equal to minus T, this behavior persists. What you find in that case is that the surface charge is no longer localized on the last site, but is in some distribution that involves many sites, several sites. And as you approach this topological phase transition, the length scale at which it's localized diverges, and that's how you actually go to the other phase. Basically, the length scale on which the charge is localized is inversely proportional to this gap. So when that gap goes to 0, the length scale diverges, and you go to the other phase. Any questions? Yes?
I just want to make sure the phase transition is at delta T equals 0.
Mm-hmm. And you can see it basically here. At delta T equals 0, this gap closes. And at that point, you cannot really define polarization because this unit vector cannot really be uniquely defined. So that tells you that that point is special. And indeed, if you say do a numerical calculation, you find that this is what happens. OK, so this is the 1D example. There is more examples that one can give, and I will move on to a two-dimensional system where this Berry curvature also has a measurable consequence. In fact, much more often measured in practice than this polarization in polyacetylene. So 2D systems. And let me start by talking about the so-called TKNN invariance. And the Chern insulator. And this is something that was first discovered back in 1982 by 4 gentlemen, TKNN. This is Howless, Kohmoto, Nightingale, and Denise. And let me give you a reference in case you want to read this. So we're not quite in 21st century, but we're coming close. And what they shown was quite startling and still has profound consequences today. They demonstrated the following fact. In a 2D insulator, let me write it like this, in a 2D band insulator, Hall conductivity sigma xy is equal to E squared over H times N, where N is an integer and is equal to the Chern number N is equal to 1 over 2 pi integral d2k over the Brillouin zone of this fxy of k, and E squared over H is the quantum of conductance. Okay. Now this H here, that's Planck constant, but not divided by 2 pi. H bar would be Planck constant divided by 2 pi. This is Planck constant as Planck originally invented it. So this is a very profound result, and let's just ponder a bit what it says. So it says that you have a band insulator in 2D. So what does this mean, band insulator? That means something like this. You have a band gap. One band, or some bands are fully filled, other bands are empty. And in addition, it's an insulator, which means that its conductivity, ordinary conductivity, say sigma xx, is 0. However, in that same insulator, Hall conductivity, sigma xy, is, or could be, non-zero. And not only that, but is quantized in a sense that it's a universal constant of nature, quantum of conductance, some 23 kiloohms if you calculate it, the corresponding resistance, times an integer, which is given by this Chern number topological invariant that we discussed previously. Yes? F is the Berry curvature that we defined yesterday. So F here is the Berry curvature. And this has been defined as gradient k cross this A of k, and I'm taking xy component of this, and this is the Berry curvature. Okay, so now what this tells you, of course, this n can be 0. And indeed, in most cases, it will be 0. But there are situations, and we will work out an example when this happens, when this n can be non-zero. And when n is non-zero, the system is called a Chern insulator. So when n is non-zero, okay. Question?
I don't understand why when n is non-zero, therefore the conductivity is non-zero. And why do we call it then insulator?
Because it's still an insulator in the ordinary sense. So if you just measure ordinary longitudinal conductivity, then it doesn't conduct, it insulates.
Oh.
But the Hall conductivity.
Oh.
Okay, how many people don't know what is Hall conductivity, by the way? Okay, let me remind you of that. So Hall conductivity you take a sample, two-dimensional sample in particular, and you apply electric field along x direction, and you study the current response along y. So sigma xy is a ratio of jy to Ex. Okay, so it's a response. You apply electric field along one direction, and you study the electrical current along the perpendicular direction. Okay, sigma xy, sigma xx here would be Jx over Ex. This is ordinary longitudinal conductivity, and that would just give you current along this direction. And in an insulator, we showed that that's always 0. However, we did not really show anything about the sigma xy. And in a kind of surprising discovery, TK and N showed that even in an insulator, this Hall response can be non-zero. Okay. So what I will do now, I will work out an example where this actually happens. And on the way, we learn many interesting things. And the example is a graphene with some special twist. Okay? So you discussed graphene yesterday, I understand, in the tutorial. So I will take advantage of that. Graphene with T-breaking mass. And what T-breaking mass means, we will explain. So let me remind you of graphene. We have a honeycomb lattice of carbon atoms again. And honeycomb lattice can be thought of as a triangular lattice with a two-point basis. So let me call these sublattice A, these guys sublattice B. And let me make the following notation. So I will want nearest neighbor vectors from site A to its three nearest neighbor sites B, and let me call them delta 1, delta 2, and delta 3. I just noticed this morning that in your tutorial you used this thing rotated by 90 degrees. This is a bit unfortunate, but I couldn't really rewrite all my notes in that short time. But this prepares you for real world where people use these conventions alternately in literature. So everything is equivalent to what you said yesterday, but it's rotated by 90 degrees. So delta 1 will be A, 0, 1, whereas delta 2, 3 will be A times plus minus square root 3 over 2 and minus 1/2. And it's a simple geometry that gives you this. So this is real space, reciprocal space. The Brillouin zone associated with triangular lattice can be taken as a hexagon. So this is the first Brillouin zone. Here's the origin. And there's two reciprocal lattice vectors that go, one goes like this. Let's call this G1. One goes like that. Let's call this G2. And the important point in this Brillouin zone will be the corners, because that's where the band structure becomes gapless. So it's this point and that point, and we call them plus K and minus K. And notice that although it looks like there's 6 of them, only 2 of them are actually distinct, because, for instance, this one and that one are connected with the reciprocal lattice vector, so they are actually the same point. So we will focus on these two. And let me just write for you the coordinates. So this k vector is 4 pi over a 1 over 3 times square root of 3, 0. Okay, and again, this is just a matter of geometry, which is kind of annoying because you have all those square roots, but that's the price you pay for some other things that we get later. Also, another point of confusion often in the literature is that this A, I'm denoting by A distance between nearest neighbor carbon atoms, but sometimes by A people denote the lattice constant of graphene, which is actually a distance between two A sites or two B sites. That's a proper lattice constant because that's how much you need to translate the whole lattice to make it invariant. And if you use that as your A naught, then there's some additional square roots that appear here to confuse the hell out of everybody. But this is the convention I will use. And if you want to practice your geometry, you can translate between this convention, the one that I just mentioned, and the one rotated by 90 degrees, and you will be a real expert in graphene. Okay, so you did this yesterday, so I will just outline some main highlights here. So what we want is the tight binding model. And again, we just use simply hopping between nearest neighbor sites, and we just take all of those to be uniform, as is the case in graphene. In actual graphene, there is also a small next nearest neighbor hopping T prime, and for simplicity, we will neglect that. So the Hamiltonian in second quantized notation can be written as, let me call it H naught, as minus T sum over ij, c dagger I, cj, where I and j go over all the sites. And this means that I restrict this to nearest neighbors. And when I Fourier transform, this can be written as sum over k, which ranges over the two-dimensional Brillouin zone, alpha beta 0 of k, c dagger k alpha, ck beta, where alpha and beta range over sublattice A and B. So this is sublattice. Okay? And I think in the tutorial you use notation A and B for creation annihilation operators on A and B sublattice. So here instead I'm using a notation where the C has an index either A or B, but it's again the same thing. And once again we see that because I only allow hopping from sublattice A to B and vice versa, this 2x2 matrix will be off diagonal. And I can write it as before, this H naught k as my d of k dotted into sigma. And I find that, once again, by just Fourier transforming, dx of k is minus t sum over p equals 1 to 3 cosine of k dot delta p, where delta p are my three nearest neighbor vectors that I specified here. Similarly, dy of k is equal to minus t sum p is equal to 1 to 3 now of sine of the same thing. And dz of k is equal to 0. The spectrum then E naught of k is again plus minus the length of vector dk, and this can be written as plus minus dx k squared plus dy squared of k, because I have no dz. Specifically, one can now do some gymnastics with trigonometry and using properties, these vectors, and simplify that expression. And I really don't want to go through that, but one can do this quite simply if one just wants a spectrum along this line here. Namely, so this is ky, this is kx. If I set ky to 0 and just write the expression for the spectrum along that line, everything simplifies. E naught kx0 can be written as plus minus t, and it turns out it's a square root of something like this, 1 plus 2 cosine kx a square root of 3 over 2 squared. So I can take that square root if I want to, and the spectrum looks like this, 1 plus 2 cosine kxa square root of 3 over 2. And it turns out that this expression here goes to 0 at these 2 points. So when you just plot it along that line, it just looks like this. So these are zeros of dispersion. And it turns out that by symmetry, there are similar zeros at the other corners of the Brillouin zone. So let me circle them as well. But there are no additional zeros. So this is an interesting band structure which has only isolated zeros in the Brillouin zone. Another important thing is that this function actually comes in linearly. So these two lines, let me just do it in another color. So what we find is that there are point zeros in the Brillouin zone at k equals plus minus capital K, that is defined over there, and dispersion is linear near these points. Okay? Now, once again, any questions about this? So, if we take this plus the following, so T in graphene is something like 2.3 electron volts. An electron volt is around 10,000 Kelvin. So one concludes that at reasonable temperatures, including room temperature, again, these guys are filled. The upper band is empty. That's from the chemistry of graphene. all the important physics will be happening near these point zeros of the dispersion, because at any reasonable temperature, you cannot really excite states up here because you would need 10,000 Kelvin to do that. But you can excite states near these point zeros. And so it makes sense to look at an effective low energy theory that only looks at the vicinity of these important points and does not have all this complexity of the lattice. Okay? And let's do just that. And we do that simply by taking this H naught of K, which I defined here, and expanding it near those 2 points to leading order in momentum. Okay. Namely, the way we do that, we take K, and let's start with plus K, and write it as capital K plus Q, with Q much smaller than capital K. Okay. And now, again, this is just a kind of grunt work. So what one does, one just sticks this in. For each K, I substitute that capital K plus Q, and I expand each of these cosines and sines to leading order in K, in this small q. And then I find that almost everything drops out, and the result looks like this. And it takes about 3 lines of algebra. And similarly for dy, and dz was 0 to begin with, so it will remain 0. So this is what happens when I do the expansion near plus k. When I do the same expansion near minus k, it looks precisely like this, but this sign here is reversed. So let me write a sign here that is plus. And is that true? Yes. And this will be valid near minus k. Okay? So the effective low energy Hamiltonian, if I now neglect these quadratic pieces and just focus on the dominant terms, is like this: H at K effective, and now let me write that as a function of Q, is Vf times Qx sigma x plus Qy sigma y. And let me put plus minus here, and there will be plus minus in front of Q, just the same thing as there, where this Vf is the Fermi velocity, and this is minus 3/2 t times A. And here I have restored A, which I temporarily took equal to 1. Now I have restored it so that my Fermi velocity has the right units. So now I conclude that the low energy spectrum in graphene has two massless Dirac points at k equals plus minus capital K. Why am I talking about the massless Dirac points? In high energy physics, maybe you saw this before. If I calculate now the energy spectrum of this low energy Hamiltonian, again, it's a two-level Hamiltonian, right? So this H F Q, and let me select the plus one here so that I don't have this, but the spectrum is the same anyway, is just D of Q dotted into sigma. But in this case, my D of Q is just proportional to my Q vector. So this is VF Q dotted into sigma. And I can easily calculate the energy spectrum of this. And this is just going to be plus minus length of this D vector. But this is just plus minus VF length of Q. And so this dispersion is simply looks like this, right? Where this is QX, QY, EKF. And this is the massless Dirac spectrum that you probably have seen in high energy physics. And there is two of them in the Brillouin zone here. We conclude that there is one such massless Dirac point here and another one in there. And they are precisely the same except for this sign that differs. So the velocity in one has an opposite sign, but the energy is exactly the same. Is there any question? Okay, so let me now do one last thing, which is a kind of organizational move. So often in the literature, you find people taking these two. So these are two 2x2 Hamiltonians, right? Because they contain these Pauli matrices. And one can combine them into a single 4x4 structure, which is sometimes useful. So we combine H plus K effective and H minus K effective to a single 4x4 structure, which basically looks like this. I take a 4x4 matrix, right? And I put zeros here, and I put H plus K effective here, and H effective minus K here. That's the 4x4 structure. So I have 4x4 matrix. And I often, or people in the literature often write it then like this. I will first write, then explain. Sigma x tau z qx plus sigma x qy. So I introduce another set of Pauli matrices, tau z, in now this what people call valley space. These plus and minus K points are often called valleys. That comes from semiconductor physics. And the 4x4 matrix is then a direct product of sublattice spaces that are described by this matrix sigma x. Remember, the sigma x distinguishes A and B sublattice, whereas tau z now distinguish this versus that valley of the Hamiltonian. So sigma and tau are Pauli matrices. In sublattice and valley spaces, respectively. So this is a compact Hamiltonian that you often find in the literature. So now, the important thing about these Dirac points is that in graphene, they are protected by its symmetries. If this just happened accidentally, then you might think that you deform the Hamiltonian in some way, or you put in slight amount of disorder, and this would go away. This low energy theory, these points could be gapped out, right? So instead of having actually a crossing point, you would open up a gap. But it turns out this cannot happen unless you break certain symmetries in graphene. And in order to understand under what circumstances you can go from here to there, we are now going to work on the symmetries of graphene. And I think this is quite useful because symmetry is a very powerful concept, so it makes sense to spend some time on this issue. In this particular case, the symmetries that protect the Dirac points are time reversal and inversion symmetry. And we will now work to understand those two symmetries. And once we understand them, we will then know how to break them. And we will then find that by breaking those symmetries, by applying certain specific perturbations to graphene, one can get some interesting phases of matter, which are topological, some of them, in the same sense as polyacetylene was that we discussed earlier today. So that's the plan. I will have time today to discuss time reversal. And tomorrow I will finish by discussing the inversion symmetry and how they can be broken. So let's discuss first time reversal. Often we denote it by capital script T. And I emphasize that this is for spinless particles. Spinless fermions. So I will disregard spin. And let me say at the outset that, of course, electrons in graphene have spin 1/2. And that leads to some additional important phenomena. But to discuss time reversal with spin is more complicated, and I just don't have time to do that. So I will do a kind of simplified discussion. But I just talked yesterday with Miles, who will be teaching explorations course in the next term in condensed matter. And he said he was interested in doing more of a topological stuff. So I'm sure he will discuss, if you're interested, he will discuss time reversals for spinful fermions, and that leads to some interesting physics. So I will give you kind of time reversal light discussion. So how does time reversal act on quantities? So first of all, time reversal obviously reverses the flow of time. T goes to minus t. Then under time reversal, we expect that position operator remains unchanged, right? If you reverse the flow of time, when this chalk is lying there, it's not going to move anywhere. However, momentum operator, we expect to go to minus p, because momentum is related to velocity, and if you see a film running backwards, then everything moves backwards as well. So now, once you take this, then you find that the operator that implements time reversal operation has an interesting property. So we want to find an operator that we call tau that will implement this transformation, right? So when we do this time conjugation operation on x, we want to get our operator x back, but for momentum, we want this operator to have a property that it reverses the sign of the momentum operator. But now we know that x dot p is minus I h bar, right? This is the fundamental commutator in quantum mechanics. And now, sorry, that should be plus. Now imagine I do a time reversal operation on the commutator, right? So I do theta x p, theta minus 1. So on one hand, what this does, it reverses the sign of p, but does not reverse the sign of x. So it reverses the sign of my operator, of my commutator. And this will be equal to minus IH, right? And if I compare the two, I come to the conclusion that time reversal operator has to involve complex conjugation. Theta IH bar, theta minus 1 has to be minus IH bar. Okay. And so from this, H bar is unlikely to change sign under time reversal, but I can. So I require that theta minus 1 is minus I. And this means that theta actually can be implemented as k, where k is complex conjugation. Okay. And theta inverse is also k, because I want theta inverse to be 1. And if I complex conjugate something to get back to the initial thing, I have to complex conjugate again. So this is consistent. So I conclude from this is that theta is an antilinear anti-unitary operator. So what this means is that one has to be careful when playing with theta, because usually when we talk about transformations like this, we're used to linear and unitary operators. So this one is antilinear and anti-unitary, which means that it has this complex conjugation in it. So I derived this in one way, but one could also write down a Schrödinger equation, and one can see there more directly that if you want time reversal symmetry, time reversal to be a symmetry of a Schrödinger equation, it needs to involve this conjugation, because on the left-hand side of the Schrödinger equation, you have I times time derivative. So something that reverses time to compensate for that has to also complex conjugate. But this is, I think, a neat way of seeing that. Okay, so time reversal symmetry in crystals. So what I want is, I want to ask a question. If I have a crystal which has a time reversal symmetry that behaves like this, how is its Hamiltonian constrained? Which terms are allowed and which terms are disallowed by time reversal symmetry? So I write my Hamiltonian as follows. So H will be sum over K, C dagger alpha K, H K alpha beta, C beta K. And as in graphene, alpha and beta are indices that could mean sublattice, they can mean valley, they can mean other things. In general, this is some matrix in these indices. This is not just graphene, this is any Bloch Hamiltonian. So this is Bloch. And I will insist that theta Cj, theta minus 1, gives me back my creation operator in real space. Now, as far as I can tell, this is not unique. One could make a different demand, and then the physics would be the same, but the expression of the symmetry would be different. But this is the simplest requirement that one can ask. And what this then leads to, when you ask how does theta act on the momentum, the momentum space annihilation operator, one finds that theta ck, theta minus 1, reverses the sign of the momentum. And this is simply because there in the definition there is e to the I k dot rj, and when you do a time reversal operation on this I goes to minus I, so you can compensate for this like that. And it also makes sense because k is related to momentum, and momentum is reversed under time reversal, so that makes sense, and one can actually derive that easily. Similarly, on the creation operator, ck theta minus 1 is c dagger minus k. Okay, so what we now want, we now want to ask the question, so what are the constraints imposed on this matrix Hamiltonian in momentum space by imposing time reversal symmetry? So in other words, we insist that theta h theta minus 1 goes back to itself, right? So this full Hamiltonian we want to be time reversal invariant. And what are the constraints that this implies for h of k? And what we get from here, so we just substitute the form of this Bloch Hamiltonian into here, and we get that sum over k, c dagger minus k, theta hk, c minus k is equal to sum over k, c dagger k, hk, ck, right? So I'm just writing the same equation, but I already substituted for this. I took into account how my momentum space creation annihilation operators behave under time reversal, so I can now compare the left-hand side to the right-hand side, and one thing that I can do, I can just say that for those to be equal, this has to be equal to that at minus k, because I can say reverse the sign of the dummy summation variable in here, and the result that I get from here is the following. So what I get is that h star of k has to be h of minus k, and this is the T invariance condition for the Bloch Hamiltonian. And again, this is spinless. Fermions. For spin-full fermions, the condition would be similar, but we would also need to flip the spin, because spin is also odd under time reversal. Okay, so let me make one last point, and let's see what does this implies for the eigenstates of the Bloch Hamiltonian. So I write the Schrödinger equation for the Bloch Hamiltonian. Looks like this. And I do the kind of usual manipulation. I insert here unity resolved as theta minus 1, and then I multiply the whole thing by theta from the left, and you can see what will happen. So I will have, I want theta minus 1 theta, like that. Theta does nothing for this E of k, but acts here on the U of k, and what I then get is theta h k theta minus 1 u star k is equal to epsilon k u star k. But by the condition on this Hamiltonian, this time reversal condition, this is nothing but this Hamiltonian has to be invariant under the time reversal. So this, in the end, implies that h of k acting so this is h star of minus k acting on u star k is equal to epsilon k u star of k. But now I use this condition here to replace this h star by the Hamiltonian itself, And finally, what I get out of here when I switch k to minus k is that h of k is equal to h of k acting on u star minus k is epsilon minus k acting on u star minus k. In other words, what this is telling me is the following, and this is the last thing I want to write. This is telling me that if uk is an eigenstate of h of k with energy epsilon k, then u star minus k is an eigenstate with energy epsilon minus k. Okay? So this is the condition on the eigenstates, and next time we will discuss the inversion symmetry and how that constrains the graphene Hamiltonian. Okay, thank you very much. Are there any questions? Okay, question?
Should the theta squared be -1 for fermions?
You have to repeat the question. Can you speak up, please?
Because I thought the theta squared must be -1 for any fermions.
No, so that would be the case. This operator here squares to +1 theta for spinless fermions, but would square to -1 for spinful fermions. For spinful fermions, this operator would look like this. Theta would be I sigma y times k, and you could see that this would square to -1. But for spinful fermions, it squares to +1. Any other questions? Okay, then thank you very much. I see you tomorrow.